This is Knowledge Engineering with Semantic Web Technologies. And this is the first extra part of Lecture 2. Lecture 2 RDF-based knowledge representations. And in this first extra part of Lecture 2, we want to talk about RDF databases. So how to store RDF data persistently. Okay, so of course, this is a very important question. So how could we do that? So the first idea, of course, is we can use already existing relational database management systems to store also RDF. Why can we do that? Yeah, sure. An RDF graph can be represented by a set of triples as a subject, property, object triple. And of course, I could create a table of 3 columns of a subject column, a property column, and an object column. And that's it. This could be how I possibly could put RDF triples, an entire RDF graph, into a relational database management system. So triples can simply be stored in an RDBMS. And why not? I mean, why should we use something else if we can, for example, here make use of 40 years of research experience in the database community? So this is quite interesting. So at least we should have a closer look in that in RDF, which can be stored in relational database management systems. So if I want to query then a relational database management system where I have stored triples, of course, Sparkle must be processed in a more complex way. So first step then should be, of course, I should convert my Sparkle query into a SQL query, of course, according to the schema that I'm using here. And then, of course, this Sparkle query, this SQL query should be carried out on the RDBMS. And in the end, of course, there should be a retranslation of the results. So I generate Sparkle query results from the SQL query results. So this would be the general way how I could apply Sparkle queries on an RDBMS. So I must transform them, I must interpret them as SQL. So we will see how this will work shortly. Okay, so now the question is, how can I really store RDF triples efficiently within a database management system? And there we will see we have 4 different alternatives that we can follow. We can put all triples in a huge monolithic triple storage. Then we could use so-called property tables, and we could also vertically partition our table in so-called binary property tables. And of course, to make indexing faster and access faster, we could use index organization, which is called a Hexastore. So we will have a closer look on that now. So first, let's have a look at a monolithic triple storage. So here, like we said in the beginning, we have one huge table with 3 columns, and we have a column for subject, a column for property, and a column for object. So all RDF triples are stored in a single table. So here you have a small example with professors and students, and you see triples here like ID1 has the type full professor, ID1 is the teacher of AI, which is artificial intelligence and stuff like that. So this could be a way how to store a graph into a huge monolithic table. Of course, this is easy to implement. This is, of course, on the pro side. And it works already also for a huge number of properties, but of course, your indices, they must be chosen with care. And potentially, you will have many self-joins, which again lead to a degradation in performance. So this is not necessarily really the best possible way. But we will see how we can improve that. But first, let's have a look at how we could implement a Sparkle select query on top of that. So here you see we have a simple Sparkle query in the blue box, and there we want to select universities of all the grad students where they have made their bachelor. So pretty simple. We have a Sparkle select. The variable of the output variable is university. We have a simple graph pattern which consists of V's, which are of type grad student. And we say these V's should have their bachelor from a university, which then will be in the output variable. So the according SQL query in the red box looks like the following. You see here we have a graph triple pattern which consists of 2 conjunctively joined patterns, triple patterns, and therefore, of course, you also have a join here in the red box. So we have both a self-join on the same table, which is here called triples. And first we name the first half or the first version of our table T1 and the second part of our table T2. So what we do here is we join the table with itself, first instance T1, second instance T2. And in the first instance, we specify the first graph pattern. We say that T1P, which stands for property, should be type, and T1O, which stands for object, should be grad student. And then on the second table, we simply look for where are the lines with, or the rows with T2 and the property bachelor from. So, and in the result, that is what we select from the second table where the bachelor is from, we select here T2O as the variable which is called university. But to really join these two tables together, I must join them with a join variable which is the subject of both versions of the table. So with T1 subject must equal T2 subject. So this is the join condition here. And you see, although I only have two graph patterns here, this results again in the first join. So if I apply more graph patterns, then you can imagine that more joins can be necessary or could be necessary. And this, of course, might result in a rather complex SQL query. Okay, so this is the translation of Sparkle into SQL if I use a generic relational database management system as a triple store, and if I'm using monolithic triple storage like it's displayed here. So first thing I can do to improve a little bit performance is, of course, in triples I'm always using URIs, for example, or huge literal values. And to speed up the join on the table, for example, I could substitute all the URIs that I use, and if they occur several times, and I could make an extra spare table which I call resource table, where I index all URIs and literals with numerical identifiers. And then I use these numerical identifiers in my original RDF triple table, which makes the triple table much more concise and makes the performance, or speeds up the performance, because then not long strings have to be stored within the triple table where the self-joins have to be carried out. So this saves space and enhances definitely efficiency. So first I separate this large monolithic table into a resource table and into an RDF triple table. So this is the first mean that I can apply. Yeah, of course, sometimes on a Sparkle endpoint, you should be able also to address multiple graphs. So how do I do that? So of course I could use several tables here, several RDF tables, but I could also use something which is called a quad table. So I don't store triples within one table, I store quads where I have one identifier which denotes or identifies the graph where the triple stems from or comes from. So this is often used to make clear the provenance, versioning, or the context of triples. So here with quad tables I have an additional column which denotes the graph where the triple comes from. This is the next step in our performance improvement. Okay, but nevertheless, many self-joins might be rather complex and rather costly. So what I could do, of course, I could think of breaking up this huge table into several tables. And the question now is, how could I organize that? The most sophisticated version are the so-called property tables, because here I try to combine all kinds of triples which share common properties. So for example, in our example, I could arrange a table for professors and I could arrange a table for students, where I sum up all triples with properties which refer either to professors or to students. So you see here I have a professor table where I have the professor who is teacher of something, and again, of course, also a professor has his bachelor and his master thesis from somewhere, and also his PhD. And of course, he has also a work relationship with some institution. And the students, on the other hand, you could distinguish between grad students or bachelor or master students. And of course, you could then say who is the advisor of that student, what is the course he takes, and stuff like that. The problem here again is also you can of course combine it with these ID-based encoding for efficiency. Of course you will need much fewer joins here. You have two different tables, and of course for many self-joins you only look in one table if this addresses only triples which refer to the professor, and only if you refer to the students you have to carry out a join. So the nice thing here is if you're already dealing with so-called structured data, you will end up of course in a relational database. But on the other hand, not necessarily for all potential values or properties there must be a triple or a value. So you might end up in your tables with many null values if not everything or all is really known for that table. But most of all, this kind of clustering, so this putting together what triples to put in which table and how to organize these property tables, this is not a trivial problem. So this is really sophisticated. So you have to put lots of effort in it to make it really efficient. And another problem is here, of course, you will have problems with so-called multi-valued properties. So here, for example, take the students. So a student might take more than one course. So yeah, you should need the row takes course either several times, or you will have multiple times a row for the same student where only the other values are either repeated or they are null. So you see, this is kind of a problem with so-called multi-valued properties in here. But moreover, clustering is really complicated. So if you try to improve it from the other side, so to make a much easier approach to split up this huge monolithic table, you could also think to create a new table for each single property that occurs. And then you would end up in something which is called a vertically partitioned table approach. So here you see for each single and each unique property we create a two-column table. So for example for the type property, for the teacher of property, or for bachelors from property, we have a unique table which combines the ideas of a professor or a student with the according object. Yeah, of course, this supports multi-valued properties and there are almost no nulls. So there are no nulls, because if there is no triple that combines a subject with an object, then of course this does not create a new row within that table. So this is quite nice. You also don't need any clustering here. So therefore, this approach much often has a very good, even an excellent performance, so if the number of properties is not growing too large. A problem here might be, first, that an insert of a triple might become complex because you have to address different tables in that. And the other thing is, for example, if you have a Sparkle query where the property value is not bound, you have to address all the tables to execute your query. And this, of course, might take a lot of time, because this then results up in a rather complex query which joins all tables or tries to join all the tables together. So queries with unbounded properties are really, really complicated and excessive in the terms of memory and time consumption for computing a result. So you see also vertically partitioned tables are not necessarily always the best choice for implementing RDF databases on top of relational database management systems. So what else do I have? What else possibilities to speed up, again, the computation of the results within my RDF graph database, which is based on a relational database management system? So we have to look at the index organization, and there we have to look at so-called hexastores. Hexastores are called hexastores because for every possible way how to combine subject, property, and object, there is an index created. So for example, SPO means the order first subject, then property, then object. POS means first property, then object, then subject, and so on. So to take care of every possible pattern that you might ask in your Sparkle query. If you look at all possible triple patterns, you must be able to quickly access all combinations of values that might occur there. So therefore, you should create an index for all possible order of subject, property, and object. And this you can achieve with a Hexastore. And there, the index is organized in the following way. So let's have, for example, a look at the SPO index. Here we have a key for the subject. This is S sub I that points to a sorted vector of property keys. Here we have N sub I property keys that are organized here as an ordered list. And each of these property keys, again, is linked to a sorted list of object keys. So this guarantees a rather fast access as you first come for looking for a specific subject, then for a specific predicate or property, and then for a specific object. If you come with the object first, of course, you might have, or you must have, another organization which starts here with the object and goes then either to the subject or to the property. The nice thing is, of course, here in our example for the SPO index, we can also use here the object part of the index of this index for the PSO index. So some data structures can reused in other indices. So this makes it a little bit more efficient. But in the end, yeah, the problem here might be that you might require 5 times as much storage as you really have available, simply for creating these large indices. And this mass sometimes really also is too complex. But on the other side, you might have pretty fast joins. So because you have an index for all possible occasion for your Sparkle queries. Of course, the performance gets worse when you require more storage, especially if you require more storage than is available in your main memory. If you have to switch to disk, then like for almost everything, performance drops, and then you might end up in problems. But these Hexastores are another possibility to speed up the processing within Sparkle RDF store, which is based on a relational database management system. So you see there are lots of tricks and possibilities to speed up RDF graph processing on top of database management systems, but there are also other approaches to implement Sparkle or RDF databases. So there are some called native RDF approaches, which are sometimes called upon graph databases or something else. So here you have some examples, Apache Jenna, for example, the Allegro Graph or GraphDB or Forstore. These are native RDF stores. And then there are these database management system backed RDF stores like Apache Jenna SDB or the Oracle server, for example. They are relational database management systems in their core. Then there is also the possibility to combine a native approach as well as a relational database approach, for example, like in the OpenLink Virtuoso or in the Sesame Sparkle database. But to get an overview what exists currently now at the market, so which kind of triple stores you can use there, the W3C maintains a list which is publicly available, and there you can access all possible either public or commercially available triple stores. So for example, the triple store where we have already applied our Sparkle queries to, so the official DBpedia Sparkle endpoint. This is based on an OpenLink Virtuoso server, for example. Okay, so this was a short excursion into RDF triple stores. The next extra part of the lecture will cover Sparkle data management, and we'll have a look into Sparkle semantics, where we will cover or develop an algebra for Sparkle, like also algebra exists for relational database systems.